All right, let's talk about one of the most critical pieces of modern infrastructure, the API rate limiter. Today, we're going to architect a system from the ground up, one that protects our applications from getting totally overwhelmed, making sure they stay stable and fair for everyone. So let's jump right in and build one step by step.
You know, you can think of a rate limiter as a really smart, really fast bouncer at the door of your API. It's standing right there on the front lines, and in milliseconds, it has to decide who gets in, who needs to wait a second, and who gets turned away. Without that bouncer, your whole system is just wide open.
So here's the game plan for this explainer. We're going to start with why this is so incredibly important. Then we'll map out the actual design, pick the right engine to power it, figure out how to scale it across multiple servers, look at some pro-level strategies, and then finally put it all together into a blueprint you could actually build.
Okay, first things first. Why do we even need these digital gatekeepers? Well, it really all comes down to one thing: protecting your system from the absolute chaos of the internet.
I mean, the threats are coming from everywhere. You've got the obvious malicious stuff, like denial of service attacks trying to flood you, but honestly, the accidental threats can be just as bad. Think about a buggy script that gets stuck in an infinite loop, or in a shared system, that one noisy neighbor who just hogs all the resources. Any one of these can kick off a domino effect, a cascading failure that takes everything down and sends your cloud bill through the roof.
All right, before we dream of writing any code, we have to have a plan. Any great system starts with a solid blueprint, one that clearly lays out what it needs to do, and maybe even more importantly, how well it needs to do it.
So, the functional stuff is pretty straightforward. First, our system has to know who is making the request. Is it a user, an API key, an IP address? Then, it's got to be flexible enough to set different rules for different parts of the API. And of course, when someone hits their limit, we have to tell them clearly, right? Send back that standard 429 too many requests error, along with some headers that let their code know what's up.
But here's the thing. Getting it to work is the easy part. The real tough engineering challenge comes from the performance and reliability side of things. This is what separates a simple weekend project from a system that can handle true internet scale. And this table just lays out how demanding it is. This check happens on every single request, so it can't add any noticeable delay. We're talking under 2 milliseconds. It has to handle millions of requests a second and be rock solid. And if the limiter itself fails, the default has to be fail open, which means we just let the traffic through. We'd rather the API be a little overloaded than completely down. It's a heck of a challenge.
So now it's time to get into the engine room. We need to choose the core logic, the algorithm that's going to power this whole thing. First up, we've got the industry favorite, the token bucket. Just imagine a bucket getting filled with tokens at a nice, steady pace. Every time an API request comes in, it has to grab a token to get through. And here's the cool part. If traffic is light for a bit, the tokens pile up. That means a user can send a short burst of requests later on. It's super flexible and great for user experience. Now, compare that to the leaky bucket. With this one, requests can pour into the bucket at any speed, but they only get processed at a fixed, constant rate, like water dripping out of a tiny hole. This is perfect when you need to smooth out traffic to protect a back-end service that just can't handle spikes. It's all about stability and cost control over letting users burst. And this really gets to the heart of it. There's no single best algorithm. It's always a trade-off. Token Bucket is your go-to for general-purpose APIs where you want a good user experience. Leaky Bucket is for when you need to protect a fragile system. And then you have other options, like the simple fixed window, which has some accuracy issues, or the more advanced sliding window counter, which is a fantastic balance for huge-scale APIs. Okay, we've picked our engine, but now we face the next huge hurdle. How do you make this work in a modern, distributed world where your users' requests might be hitting hundreds of different servers? Yeah, if each of your servers keeps its own little counter, a user could just blow right past the limit by spreading their requests around. It's a non-starter. You absolutely need a single source of truth, a centralized place to keep all the counts. And for that job, pretty much everyone turns to Redis. Why? Because it's in memory, which means it has that sub-millisecond speed we desperately need. But using a central store creates a really nasty problem, a race condition. Just follow along here. At the exact same instant, server A and server B both ask Redis for the user's count. It's 99. They both think, great, one request left, and they both approve of a request. Server A sets the count to 100, and then server B sets it to 101. Bam. our limit of 100 is completely broken. This is a massive flaw. So, how do we fix this? The solution is as elegant as it is powerful. We use something called atomic operations. Atomic just means the entire process of reading the count, checking it, and updating it has to happen as one single unbreakable step.
And this is where Redis and a little language called Lua become our heroes. When you wrap all your logic, the read, the check, the update, inside a Lua script and send it to Redis, Redis makes a promise. It guarantees it will run that entire script without letting any other command sneak in. The whole thing becomes indivisible. And just like that, the race condition is gone. It's the secret sauce that makes this whole thing work at scale.
Okay, we've designed a pretty solid core system. But when you're operating at the kind of scale that a company like Netflix or Uber does, you need even more layers of defense. So let's look at some of the battle-tested strategies that the real giants of the industry use.
This is a brilliant idea from Netflix. They basically said, what if we stop just counting requests? Instead, their system monitors the actual health of the service by watching how long requests are taking. If latency starts to creep up, that's a signal that the system is under stress, and the rate limiter automatically tightens its grip. It's proactive, not just reactive.
And for when things get really, really bad, you have to move from just limiting traffic to actively load shedding. The idea is simple. Not all requests are created equal. So during a major outage, you can start intentionally dropping less important traffic, say requests for background analytics or fetching movie trailers, to free up every possible resource to make sure the critical stuff, like actually streaming a video or processing a payment, stays up and running.
Finally, a really robust system is also a good neighbor. For years, every API had its own weird custom headers for this stuff. Now, thankfully, we're moving towards a standard. And using these standard headers is huge because it lets client applications be way smarter. When they get blocked, they can look at the reset header and know exactly when it's safe to try again, instead of just hammering your servers with useless retries.
Phew, okay. We have covered a ton of ground. So let's bring it all together. Let's synthesize all of these ideas into one final actionable blueprint for a system that's truly ready for production. So here it is, our blueprint for a multi-layered defense. At the very core, we're using Redis with Lua scripts for that atomic, race-condition-free state. We're choosing the flexible token bucket algorithm to manage the normal flow of traffic, but we're adding load shedding as our emergency brake. We're going to place this whole system right at the edge of our network, and we'll design it to fail open to keep the lights on. And finally, by using standard headers, we create a system that works with its clients, not against them. That right there is your checklist.
So we've designed our Gatekeeper. It's powerful, it's scalable, it's resilient. But it does leave us with one last question to chew on. In a digital world that is constantly changing, with new threats and new traffic patterns popping up every single day, is any defense ever really finished? Or is building a resilient system a process of constant, never-ending adaptation? Something to think about. Thanks for joining me on this explainer.